Okay, so in this exercise we're going to look a little bit further at calculating probabilities, but it is just like I mentioned in the last exercise where you just find the area under the curve. But before you don't watch this video altogether, there is one thing that we're adding here, and that's specifically about a uniform distribution. Okay, so you do need to watch this video as well. It is very easy. So first of all, these are on your reference sheet. Now that are there. A lot of the textbooks use X because when the original reference sheet came out, that was an X. One of the reasons it was changed is when you integrate this, you get X's. It can get a little bit confusing because you've got X's all over the place. So the R can help with that. A is where the domain of the function starts, so where it's at 0. It is interesting to mention that in my very first video on this topic, I talked about the functions not touching 0. That was in specific reference to what we call the normal distribution that we're going to learn later. But in some of these distributions, they can touch 0. And then this is page 2 of the reference sheet. And then this is exactly what I was doing in the last exercise as well, where the probability of being between A and B is just the integral from A to B. And A to B must be within the domain that the probability density function is defined on. Okay, so let's have a look at uniform distributions. So a uniform distribution is where all outcomes are equally likely. Now, we looked at this in year 11 with discrete probability functions. So we looked at specifically, for example, rolling a die where each outcome is equally likely. We're now looking at it in terms of continuous probability distributions. So it has to be something which is a continuous measurement. I actually had a lot of trouble finding some real life examples of this. One real life example would be if you're finding a random number where there's infinitely many decimal places, your random number it is a continuous measurement, so it's not rounded off. This is quite similar, this example. So we've got a point that's chosen at random between 2 centimeters and 8 centimeters away from another point. So you've got some point here, and you can choose any point, anywhere, but it has to be more than 2 centimeters away, but less than 8 centimeters away, and it's completely random where you choose that. So it's uniformly distributed between 2 centimeters and 8 centimeters because every point is equally likely to be chosen. So the way we draw the probability function for this, because every outcome is equally likely, we start at 2, we finish at 8. The probability of each of those is exactly the same. So our function, the height of the function is going to be the same everywhere. You end up with these rectangles. So as you can imagine, finding the areas for these is very simple. Okay, now we do need to work out the height of that rectangle, and to find the height of it, we have to make the area equal to 1. So this distance is 6, so that height must be 1 on 6. And the formula is 1 over b minus a. So in this case, b minus a is 8 minus 2. 1 over 8 minus 2, which equals 1/6. So then it's very easy to find these probabilities down in part C, but let's just have a quick look at part B. We have to express this PDF in function notation. Okay, so the probability is, so remember the function is the probability. So we're stating the probability of our outcomes. So the probability is 1 on 6 if x is between those two values of 2 and 8, and 0 for all other x. Now to find these probabilities, you could integrate that if you wanted to. You'd get x on 6 and you plug in some numbers. So it works exactly the same way. And if they give one that's not uniform, that's how you're going to do it. You're just going to integrate it. So let's have a look at the probability that x is less than 4. So up in our diagram, we're just looking at the area under the curve from 2 to 4. Okay, so very simple. So the base is 2 times 1/6. So so it equals the area from 2 to 4, which equals 2 times 1/6, which equals 1/3 chance. Okay, which makes sense. It's 1/3 of the rectangle. So the probability it's between 3 and 7 works in exactly the same way. So it's just our 7 minus, sorry, I wrote times, I meant minus. So 7 minus 3 gives us the base of the rectangle times 1/6 for the height of the rectangle. So 4 times a sixth is 2/3. The probability it's greater than 7. So you could do 1 minus from 2 to 7, or we can just look at this little area here. So it's 8 minus 7 gives the base of the rectangle times the height of the rectangle. So 1 times a sixth, that probability is 1/6. You can see that's pretty straightforward.